It's my pleasure to continue the conference with the talk by Dierk Schleicher from University of Marseille, who will talk about postsingularly finite entire functions, combinatorics, complexity, Thurston theory.
So thank you very much. Hello to everyone near and far. First, thank you for giving me the preferred spot. We all just had a bit of fresh air for the picture and got fresh coffee. So what could be a better situation? But really, I would like to thank the organizers far more seriously. It's been an effort, of course, I speak from experience, to organize a conference in the hope that it will take place. And it's not clear, will it be, how can we do it? And then to run it in hybrid mode. This really makes a difference. All the inspiration in my own talk. So yes, Artyom, you nicely read the title I was planning to speak about. But last week, I was not only organizer, I was participant at the conference. And there were so many personal discussions so that in preparing this talk, the topic grew on me and developed further. So the title has changed and the content has moved because of the interaction we had in person last week. And I very much hope the spirit will continue this week. I just arrived, so I cannot judge, but I'm sure it does, so that the personal interaction that we can now have will help us to move forward in what we love to do, which is mathematics. So thank you, Felix, Artyom, Piotr, David, and whoever else was responsible for making it happen. Feels very great to be here. So I will talk about various aspects of geometric complexity. I was reflecting a bit on the topic of the conference in relation to what I had done or what I'm interested in doing in various contexts. So first, I want to talk about complexity in terms of branch points or biaccessible points in Julia sets, which is work I had done before chapter 2. Core entropy was introduced by Bill Thurston. I want to report on this specifically for polynomials. And the third topic is, hey, many of us live in the transcendental world to see how far we can move from polynomials to transcendental mappings, which concepts apply or do not apply. And here there are some quite recent results and some open questions to report on. So let's start easy and with pictures. I've just included some more or less random or not so random quadratic polynomials. And you see, well, and you all know, I mean, they're very well branched, and complexity somehow, an interval is not really branched or a circle. And then you can have lots of branch points. So one way to measure the complexity of a Julia set is how many branch points there are. So a typical point in the Julia set, is it an endpoint, a branch point, or something in between some inner points? And the definition that I'm going to use is a biaccessible point. The point is biaccessible if it's the landing point of at least two rays. So you have one ray here and one ray here that lands at the same point. In this picture, there are some endpoints more than others when only a single ray lands. So biaccessible is when you have two or more points that land together. And we measure this, well, in terms of the rays, and every ray has an external angle that lives on the unit circle. So, well, then there's obviously an issue. Do the rays land at all? What if they don't? But the rays that don't land have dimension 0, so they don't really play a role. And even for those, you can get around by combinatorial ways. So landing or not is not really an issue. Moreover, 3 or more rays land together only at countably many points. So really the rays that form triples or more are negligible. And it's really endpoints versus biaccessible in the sense of doubly accessible points. Hey, and Anna, I have the pleasure to cite an old result of yours, which somehow makes me reflect, hey, we've known each other for quite a while. So what implications does this have? And well, it doesn't feel like 20 years, but somehow, well, time does move on. So the earlier results that I know about this topic, the 3 results don't prove exactly the same thing, but they're similar in spirit, that biaccessible points have 0 harmonic measure for well, quadratic or even arbitrary degree polynomials. Sorry, no, it's all wrong. just the opposite. No, it's exactly the way it is, yes. So 20 years. So I have the expert sitting here, yes. Biaccessible points are rare, except I should have written when the Julia set is an interval. So in general, that almost all the points are endpoints, which is a bit funny. If you draw a finite tree, then there are only so many endpoints, and then the more branches you add to the tree, you add more branch points, and in the limit will all the inner points vanish, and you only have, almost only have, endpoints left over. So let's turn this into combinatorial language. An angle, as I said, it lives on the unit circle, is biaccessible if there exists another angle so that the two rays of these angles land at the same point, or combinatorially try to land at the same point. It's just the same. And then I define the biaccessibility dimension of a polynomial Julia set as the Hausdorff dimension on the unit circle of the set of angles which are biaccessible. So this is a subset of the unit circle, and as such, this dimension is between 0 and 1, and it's included. Now I'm happy to report of a bachelor thesis of many years ago, a bachelor student at the time, Philip Meerkamp, who went on to do his PhD in Cornell with Guggenheimer. The biaccessibility dimension of any polynomial with Julia set is less than 1, except, and I should have stated this except on the previous theorem, if the Julia set is an interval. So there are no topological hypotheses on the Julia set. It doesn't need to be locally connected or any degree or anything. So this is, in a way, a strengthening of the previous result. Well, it came quite a bit later, of course. If the biaccessibility dimension is less than 1, then of course the measure in dimension 1 is 0, and the measure in dimension 1 is exactly the harmonic measure. So this makes us even stronger that if you're not an interval, then very much most of the points are endpoints. So, and this dimension is a way how to, well, I don't want to define complexity precisely, but this is one way of defining it. Then with Henk Boyne and myself, we had studied this biaccessibility dimension quite a bit in more quantitative versions for quadratic polynomials only. So the biaccessibility dimension, of course, can be 0 when you have a circle or topological circle where there are no two rays land together. Or you can have, well, something like the basilica. Well, what can you see here? Here's a little basilica. And you only have countably many biaccessible points. And so the biaccessibility dimension is still 0. So this is kind of obvious. We have for quadratic polynomials with connected Julia set a precise condition that this dimension is 0 if and only if the polynomial is from the closure of the main molecule. So the main molecule is when you bifurcate in the Mandelbrot set. Well, this is what I just shown here is the bifurcation from 1 to 2. And there you can go to 4, 8, 16, and so on towards the Feigenbaum point, or rabbit or whatever. But it's also 0 in the limit when you get to, well, an endpoint of those. For instance, the biaccessibility dimension is 0 even at the Feigenbaum point or any of the other limits of bifurcation. In fact, I can offer you, I will not go through details. We can estimate this reasonably precisely. And just to show you, I'm not sure I want to get into details. But the fundamental idea is you look at a quadratic polynomial in the Mandelbrot set, and all you need to know is the Kneading sequence. Well, the external angle of the ray gives you immediately the Kneading sequence. It's a sequence of zeros and ones. And what we need, and by convention, it starts with 1. So it's a sequence of the kind 1, 0, 0, 1, whatever. And what we need, this n here, is the position of the second one. The first is always at the beginning. And all you need to know is the position of the second entry, 1, which we call big N, and then little m, big M is essentially half of it. And then out of these two things, you can define a lower bound and an upper bound for the biaccessibility dimension. This is the first set of lower and upper bounds only in terms of the position of the first one and of the second one. And you get another set of lower and upper bounds when you look at bifurcation. So the internal address, for those who know, and again, I didn't want to go too much in detail, is the kind of, well, it's a strictly increasing sequence of integers that tells you which hyperbolic components you have to pass through when you go to a particular one. For instance, the Feigenbaum point has the internal address 1, 2, 4, 18, 1, 2, 4, 8, 16, the powers of 2. And you stop at the time when it's no longer divisible by the predecessor. So in a way, it's infinite if you're still in the closure of the minor hyperbolic component. And then, well, this upper bound applies. So in the main molecule, you get 0. And it even gives you some kind of continuity in the neighborhood of the main molecule. There's a lower and an upper bound. So it really tells you how close you are to 0. So in fact, it gives you, well, something like, it gives you continuity at those parameters for which the dimension is 0. Okay, so that is one way of defining and investigating complexity of polynomials, with the second result being for only quadratic polynomials. I kept a few empty pages in case there are questions, and I should draw some pictures, so I made some space for me. So that was the first topic, and it's a good time to ask whether there are questions or comments at this time. Because then I started with a topic which in some sense is very different, and then it turns out it's not so different. And this is core entropy. I don't think I have to define topological entropy in Poland. It would feel a bit, very unnatural to define it. Later on here in Poland, there's expertise enough. I'll get to some comments later on, so perhaps students get to see it also. But I would like to start with the theorem of Michał-Lubitsch from the 80s. If you have a rational map of degree D, then the topological entropy on its Julia set depends only on the degree and is log D. A very nice result. You only need to know the degree. On the other hand, since it's constant, it's not the world's most interesting map throughout parameter space. And it was known in the real case that had been investigated long ago. If you have real unimodal maps of this kind, lambda x 1 minus x, then you have a dynamical interval here. And the entropy, the lambda can be between 0 and 4, the way you normalize it, in the interesting case. If you change the parameter, then the entropy on this real interval is strictly between 0 and log 2. Not strictly, it's between 0 and log 2. So in the reals, it's in a way much more interesting because it varies and can distinguish the maps. And it was known to be monotone with respect to lambda. So the difference to the complex point of view is co-occur entropy on the if you have a real polynomial, you don't look at the whole Julia set. You only look at the intersection of the filled Julia set with the real line, with this dynamical interval here. So it's an invariant subset that carries the interesting dynamics. And then you have more interesting, you have a different concept of entropy. I don't want to say which one is more interesting. You have a different concept. And Thurston has generalized this around 2010 from the real context to polynomials, more precisely to post-critically finite polynomials. Because if a polynomial is post-critically finite, then the Julia set is connected and has an Hubbard tree, which is an interesting forward invariant subset of the dynamics. Interesting in the sense it captures the dynamics of the critical orbits in plural if the degree is higher. And interesting in the sense that if you know the Hubbard tree, you know the polynomial. So you have an invariant compact subset, and then of course you can consider the entropy restricted to this invariant compact. And that's what Thurston defined as the core entropy. Core is the dynamical core of the Hubbard tree, and the entropy on this. So that was a new concept, and he asked a couple of questions about this. And well, then there was the issue how much. So, well, let me start differently. I just checked in 2010, I received an email from Bill who told me, oh, I'm going to study this core entropy. He had some pictures, he had some questions. And he asked me for opinions and for ideas and such. And I was embarrassed because I felt I had nothing to say about it. And so I failed to respond for quite a while until I learned much later that in fact, core entropy is the same as the biaccessibility dimension in cases where they're both defined. So this is a message that reached me from Thurston out of the hospital, where unfortunately already was at the time. And it's not very hard to see this once you know how to do it. So Bill Thurston observed this. The only written proof that I'm aware of is by Wolf Jung, but the result really is, meanwhile, it's some kind of folklore. So this issue of biaccessibility dimension that we had studied before really is the same. So it's not a new concept. It's the same as core entropy, except for scaling factor. But there's one conceptual difference, and that is if you don't have a Hubbard tree, it's not so clear what the core entropy should be, while its biaccessibility dimension is defined everywhere. So you don't even have, if you do it carefully, you don't even have to have connected Julia sets. So it's a concept you can define in purely combinatorial terms throughout parameter space. And then Thurston asked this question, is core entropy, I think he was talking about quadratic polynomials at this time, is it continuous as a function of the complex parameter? I happened to spend the spring of 2012 in Cornell. It turned out to be Bill's last semester. And he and Hubbard were discussing it quite a bit, and they made a bet, $20 whether or not it's continuous. Bill thought it was, and Hamill was worried, but what about parabolic points? And then, yeah, what is the connection? What is the similarity between the name Thurston and the name Dudko? Well, there are two well-known mathematicians, each with these names. And so there's Bill and there's Dylan Thurston. And this Dudko is not Artyom, it's Dima Dudko. We worked on this in the semester, and by the end of the semester, we made enough progress that we saw John Hubbard pay $20 to Bill Thurston. So somehow that issue was settled at the time. We published this a bit later, independently. Julio Chiozzo had his own somewhat different, quite different proof that he published a bit before us. In any case, the result is the same, that core entropy is continuous throughout the space of complex quadratic polynomials. It's interesting that Julio and Dima and I had different definitions, different extensions of the entropy from the post-critically to the finite to the infinite case. But we both prove continuity. So in a posteriori, these definitions actually coincide. And then later, Chiozzo together with Gao extended this result also to higher degree polynomials. So in some sense, the story is closed for polynomials. Now let's move on to the transcendental world. How much of this theory can you extend from polynomials to transcendental entire functions? So the natural idea is, well, take yourself a Hubbard tree, for an entire function, maybe postsingularly finite, and then do the same machinery. Unfortunately, Hubbard trees do not exist in general. In particular, so this is the dynamics of a postsingularly finite exponential function. I think it's the map z maps to I pi e to the z. So let me try to convince you that there cannot be a Hubbard tree for this map for any postsingularly finite exponential. It is known that the singular value, I think here is the singular value, is the landing point of a periodic dynamic ray, a pre-periodic dynamic ray. It's known in much greater generality now by work of Helena Mihailovich-Brandt that this is a very general result if the singular values are periodic or pre-periodic. So a ray lands at the singular value 0. Now this ray has countably many pre-images, which all land at the pre-image of 0. Well, what's the pre-image of 0? It's kind of minus infinity. So we get countably many rays of this type. And they happily disconnect the plane into chunks, strips of height 2 pi I. And all the points in the ray escape to infinity. Now, if we try to draw a Hubbard tree, it must connect the post-singular points. And so it must sum, in particular, these two post-singular points have to be connected, but they have to be in different strips. And they cannot be all on the same strip. So how do you connect this point to this point, this one here to this one? By a compact invariant set. Well, the connection must run through the boundary of the strips. So it must intersect an escaping point. And so there is no hope for invariant compact set if you have escaping points. So that shows that there cannot be Hubbard trees even for exponential functions. So that approach doesn't work. And also with external angles, you have rays, you can parameterize them using external addresses. We know quite a bit of those. But it's much easier to have an invariant measure on a finite set, or maybe a set of 2 elements for quadratic polynomial 0 and 1, than for an invariant set, the integers that label the external addresses. So it's not clear to me how to deal with the biaccessibility dimension, even for exponentials. Okay, topological entropy, however, can be defined for entire functions. And there's a very recent result, Anna Benini, Eric Fones, and Han Peters together showed that in analogy to polynomials or rational maps, if we consider the degree as infinite, then the topological entropy is also infinite. So it's constant, always the same, but doesn't help us to distinguish. So what can we do to make sense of this anyway? So let me move to the PhD thesis of a former student of mine, David Pfrang. And in a way, in his first part of his thesis, he proves that Hubbard trees don't exist for entire functions. And in the second part, he proves that they do exist. And the difference is you have to give up on this invariance condition and replace it by the concept of a homotopy Hubbard tree. A homotopy Hubbard tree is, well, this is why I have some space here. So this is supposedly a Hubbard tree, and we have to map the tree with the continuous dynamics that has to respect the edges. So when you take an edge from here to here, its image maps over one or several edges, but fully over the entire edges, and doesn't stop halfway in between. So he allows homotopy in the sense that the image may not be an edge, but in a way it's homotopic to an ends in an appropriate sense. So this issue of escaping points on the tree, he always homotopes away in every step, which is very natural because trees are about classification. You don't want to know them as precise subset of the plane, really you want to know them only up to homotopy. So in hindsight, Thurston theory is only about homotopies, or of maps up to homotopy. So in hindsight, this is the natural thing to do. But of course, you have to deviate from a firmly established concept that a Hubbard tree wants to be invariant. So perhaps the main result of his thesis 2 years ago is that every postsingularly finite transcendental entire function has a homotopy Hubbard tree. That is a finite tree, invariant up to homotopy. And it's also unique up to homotopy. So out of the map, you can extract the tree. And conversely, if you know the tree, you can reconstruct the map. So the whole thing, Nuri, I can send you the slides afterwards if you want. Yeah. Okay. Whichever way, yes. Next time I can smile for you in front of the picture, then I'm better. Okay. Okay, fair enough. Oh. Okay. So this is what David contributed. And I think this is going to be a most helpful ingredient in quite a bit of work that we want to do about transcendental dynamics. I mean, it's hard to imagine polynomial dynamics without Hubbard trees. And now having the Hubbard trees in the transcendental world, I think we're just at the beginning of really comprehending what this gives to us. So in particular, what it does give to us, if you have a finite tree, which is in some sense combinatorial invariant, you can define topological entropy on this tree. So what you really need to do, let me go back to this picture. You make a matrix, here are the edges, and here are the edges. And then the map goes from one side to the other, says this edge maps over this and this and this edge and not over the others. The next edge goes over whatever. So it's just the transition matrix, which maps goes over which other map, which other edges. And well, it doesn't care about homotopies as long as you know where the endpoints map and you have a tree. And then you can just, so one of the takeaway messages from this talk is the more you do in terms of symbolic dynamics, the less you have to worry about topological issues. And so you translate this into a matrix, a transition matrix. And then one of the standard, now I am giving a definition of core entropy. One of the standard definitions is simply the leading eigenvalue of this transition matrix, which by Perron-Frobenius is always non-negative real. So just out of David's thesis, we weren't thinking about it at the time. It becomes apparent that you can define core entropy for every post-singularly finite transcendental entire function in a natural way, just like we've always done it. And then you can ask, Nuria?
In the 2 pi I map that you mentioned at the beginning, what would be this finite tree up to homotopy?
So yes, let me try to see whether I can reconstruct it here. I haven't looked at it for a while, but in some sense it's natural. And the interesting thing is you see that in this picture nicely, there is a periodic point that's the landing point of 3 rays. You see this guy? So this wants to be a branch point in the tree. So we go through this point. This point is nicely invariant and it will be a fixed point of the tree. Now, what are the points that we have to connect? This is the singular value here. We connected avoiding these branch points. And then I think that's just 0 maps to I pi. So we have to connect it there and it maps to minus I pi, something like this. It's a candidate. And if I move quickly, you will not find if it's inconsistent before the talk is over. But it's something like this. The idea in the proof and the whole concept is you want to find enough repelling periodic or pre-periodic points that give you structure that the tree has to run through those. And that way you find all the branch points in the tree. And when you have enough of those, then you can, there's a unique way to connect, a unique way up to homotopy, and that's what he does. So the key issue are the branch points that you identify by landing points at repelling periodic or pre-periodic points. I have another example coming up on one of the next slides, but it may not be quite so convincing or so revealing, like this one. So let me give you some results throughout parameter space. If you're not, so every individual post-singularly finite map has well-defined core entropy. But what if you change the parameter? The first result, another former bachelor student of mine, Malte Hassler, is that if you have exponential maps, core entropy is always bounded above by log 2. So even though it has the infinite degree, core entropy doesn't get better than quadratic polynomials. In fact, what he observed is that if you look at unicritical polynomials, then even though the degree is higher, and for degree d polynomials, entropy can get higher. In the unicritical case, so if there's a single critical point in C of higher multiplicity, again, the upper bound is only log 2. So these are natural parameter spaces where the core entropy does not explode. On the other hand, when you look at cosine maps in the cosine family, then you can very easily get maps for which the entropy diverges. That's an observation of Bernhard Reinke. And I have to get used to no longer saying he's a graduate student of mine, because he finished with a PhD, so he's a former graduate student of mine. So multiples of cosine, real multiples. So where is space? Here. And the idea is simple. You have cosine, and now I want to take some integer n. So this is pi n. And if I multiply appropriately, then this real interval is invariant. Cosine maps the whole line to the interval between -1 and 1, multiplying by pi n maps the whole real line from negative pi n to plus pi n. So this interval is certainly invariant. And now we have many laps like so, which map to 1. So it's just a prototypical example. Every point has n or 2n pre-images. And the entropy really is, so where are we? The entropy in this case is log of 2n or something. I think I have a picture and more explanations on the next slide. So there's a fundamental difference between exponentials and cosines. And they're also kind of the opposite end of the spectrum. The exponential has one singular value and one pre-image, so to speak, at minus infinity, a single critical point of infinite degree, so one critical point of huge degree. While cosine has infinitely many critical points, but all simple critical points. This is the opposite end of the spectrum. And as far as core entropy is concerned, they are quite different. So specifically about cosine maps, I would like to advertise the work of a current graduate student, Chernov. And he has two, again, complementary results that produce some tangent of how to understand the family. First is that core entropy is even locally unbounded. So there is a sequence, a convergent sequence of parameters, lambda n tending to a limit in the complex plane. Not the infinite limit like in the previous slide, limiting complex numbers so that the entropy tends to infinity for these lambda and cosine z maps. So locally in a small neighborhood of this limiting parameter, the entropy is unbounded. All of them have finite entropy, but they go off to infinity. In fact, you can do this for all lambda infinity, for all limit points in the complex plane. for which, so that at the limit point, the singular values escape to infinity on rays. And I think this result has quite a bit of potential to generalize to many transcendental mappings. So Roma, I think you hear me, look at this. This should be a result for a large space of transcendental families with many singularities. However, the kind of opposite result of Roma is if you restrict the combinatorics to spaces of uniform bounds, take a uniform bound and then take parameters within this uniform bound, then not only is it bounded, but you get continuity within these restricted parameter spaces. So we heard in the previous talk, regular external addresses that were defined by Devaney in the probably previous century even. So if you do something similar here, call it, no bounded, not regular is a different thing. The bounded ones, if you consider uniformly bounded ones, then entropy respects the bound. It can be explicit here, and you even get continuity. Here, this is elaborating on ideas by Giulio Ciozzo. Okay, let me try to give you some ideas. I think I have about 10 more minutes if I get this right. 10 plus epsilon, okay. So let me try to give you some ideas of why these previous transcendental results are true, especially Malte's idea of exponentials that the entropies always log to. Now, I do want to define core entropy, or more precisely, give you a few ways of looking at them in different ways. And for some, it's easier than for others. The first definition I had kind of anticipated earlier. You have the transition matrix between the edges, and then you take the log of the leading eigenvalue. This, in a way, is, well, it's not how it's defined, but Mizerevich and others, I think Yom, have a paper that show that this is really the same as topological entropy on the tree. Another definition is the asymptotic number of preimages of a typical point. You take some point in the tree and you count how many preimages there are of any kind of generation. And the number of preimages will grow exponentially, and the log of this exponent, this growth exponent, is again core entropy. In particular, a special case, but this is the one that Malte likes to work with the best. You take the critical value or the critical values, and you look only at the preimages of the critical values of any given depth, and again, the exponential growth rate. And then one last definition, it's all the same, and you'll say, well, what's the difference? I don't claim there is a difference, but some appeal to different aspects of your intuition than others. The number of combinatorially different orbits, well, let me just say it. We distinguish two orbits of length n if, as you iterate, they go to different sides of the critical points. And then you asked how many orbits, how many essentially different orbits there are of length n. And of course, you increase n and take the log, and well, the exponential growth rate. So orbits are different if they're different sides of a critical point. And this last thing you can do, so here's some space. Let me erase a bit. I should have added another page. So I have some kind of tree. Let me introduce some critical points, like so. And now I start with some segment here. All the points are in the same set of all critical points, so they seem to be the same. Then the image, maybe it's here, still the same, the image is there. And let the next image be kind of this one. So then what we say, we cut it, like, I mean, there's a Hofbauer-Keller, very old work on cutting times. You cut here and only take two separate intervals. and continue to map those forward injectively. So one of them may go here and the other perhaps there, and then you cut again and so on. You start with an interval, you keep iterating forward while you can do this injectively. And as soon as you run over a critical point, you cut it off, and then you run the two parts separately again injectively. And then you count the combinatorics, how often you cut off, and do this as you go off to infinity. Why is this so interesting? Now, if you take another Hubbard tree, unique critical Hubbard tree, then it looks like this. You have a big critical point in the middle. And when you do this algorithm, start somewhere here. Every time you go through the critical point, you cut only in two parts. So even though you have degree D available, D minus 1 critical points, you cut or you don't cut. That means in every step, you can at most double the number of intervals you get. And well, if the increase exponentially is bounded by a factor of 2 everywhere, well, then the entropy is bounded by log 2. So this is the essential reason why for unique criticals and for exponentials, maybe to some people it seemed quite counterintuitive, but still why you get the uniform bound of log 2. This is the slide which describes what I just explained to you. So if you have a single critical point, then you get a natural bound of log 2 for the entropy. Even if the single critical point is somewhere out there at infinity and your tree has to go through infinity, up to homotopy, it doesn't really matter. Now the question is, how much further does this carry you? And this is a result, I mentioned this earlier, that really was inspired by last week's conference and discussions. When we could all meet and discuss and talk, you realize, in fact, you had something quite a bit more powerful in your hands. If you have structurally finite transcendental entire functions, then core entropy is bounded uniformly throughout parameter space. So all this depends, of course, on the definition of structurally finite. And it means you have finitely many critical points and finitely many asymptotic tracks. An asymptotic track kind of is a critical point, infinite degree, out there at infinity. So, and once you have just this definition, then quite clearly, finding many critical points, well, you take your interval, you keep iterating. You can divide it only so often. In fact, if you have critical points in the finite plane and at infinity, then the log, count the number of those, then the entropy is naturally bounded in terms of the number of critical points. So these are transcendental parameter spaces for which you get uniform bounds on the core entropy. So the cosine thing, well, I had mentioned this before. This is, and I think I have an empty slide there where I wanted to know down here. That was where I planned to draw Bernhard's example. But I mentioned this earlier. So you can get arbitrary large entropy in the cosine family. And as I also mentioned, there's quite a bit more results to come out of Roma's thesis. So Roma is the man to watch. Before too long, I hope we have interesting things to present in this thesis. So as I near the end, I wanted to conclude with a perspective and a connection to what I was originally planning to talk about. What is unbounded core entropy beyond the cosine? So Bernhard had this very nice example where you see for the cosine, it's quite natural that the entropy can grow big. But if you have, in principle, a family where you have infinitely many critical points or asymptotic tracks, a priori you would expect that the entropy is unbounded if you arrange things right. What does it mean to arrange things right? So here is one problem observed also by Bernhard just the other day. when you take the second iterate of the exponential, then you have infinitely many asymptotic tracks. So somehow it's not structurally finite anymore. So you would expect from this line of reasoning that core entropy was infinite. But it's not. It's the second iterate, so the entropy is only twice as big. And that is in some sense because you have a lot of critical orbit relations, so that many of the critical points map onto just one. What you need is a linear set of critical points that are not star-shaped, but really aligned so that the image of an interval can reach many of the critical points together. So the big question is, you have your parameter space, which is not of structurally finite type. Can we arrange it? Are there examples where the entropy is bigger and bigger? So in other words, given the Hubbard tree in such a map, can you produce Hubbard trees? Topologically, it's easy to produce a Hubbard tree for which the entropy is bigger and bigger. And the big question is realization theory for Hubbard trees of transcendental mappings. And now that brings me to one of my favorite topics. Well, core entropy was Thurston's invention, but Thurston theory often refers to his realization theorem for rational maps with certain properties, up to homotopy as always. So we need a realization theory for transcendental mappings, given some sketch like a Hubbard tree, show that there exists such a map, in particular, so that you can produce, in this context, one with big entropy. I think I have to skip this. I wanted to convince you that you can define core entropy in a purely combinatorial term rather than through when you have Hubbard trees. Even in the post-singularly infinite case, Malte's definitions make perfect sense and give you a definition of core entropy in parameter space. Well, this is for some other time, I guess. So the last conclusion on this slide in any case is core entropy is defined combinatorially throughout parameter space if we do it combinatorially. So, and then maybe I want to conclude by stating, in order to really answer questions like unbounded core entropy, what we need is a theory for transcendental mappings of this kind of turning topology or Hubbard trees into realized maps. And this is exactly the ongoing work of Sergey Shemyakov, another one of my graduate students, who has managed, so Thurston's theorem was on rational maps. And in the early 80s, John Hubbard, when he first learned about it, immediately asked, can you do something for transcendental mappings? And nothing happened for 20 years or so, until then Mitsu Shishikura, Hubbard, and I were able to extend it just one step further to exponential maps, which at the time we were very proud about, but it's just the simplest of all, or one of the simplest transcendental mappings. And now Sergey comes about and has, do I have? Here. He has Thurston theory, again, for structurally finite topologically transcendental maps. He can produce Thurston theory, which I think is a big progress, but for our context, it's exactly the ones for which we know core entropy is bounded, but he has still some stability under compositions so that he can get, for instance, to the cosine family and classify the Hubbard trees that you get if you weren't using these simple ones. This is work in progress, but quite exciting work in progress, that this characterization theory of Thurston works for a large class of transcendental functions. And I hope we'll soon have an opportunity to present some more about this. But I think I've used my time, and we've all used up the coffee that we needed to go through this talk. So I'm very happy again to be here, and I think that this complexity of Julia sets, really thinking about it, is, well, quite close to what we have been in the making for quite a while. So I thank you for your attention and hope for questions.
Thank you very much for a great talk, indeed very much related to the topic of the conference. So any questions, comments from the audience here? Maybe from online audience? I guess coffee very enough.
Yeah.
Okay, let's thank Dierk again.